Hello folks, we're back with more math. Today we're going to continue our journey into line integrals. We've been doing work integrals for a while. Last time we did also flow, circulation, and flux. Today I want to go back to work integrals. We've seen the only way we've seen to be that we could solve them was basically parameterize the curve and use the parameterization to solve the work integral. Now, when we have a work integral of the form f dot dr, remember this is what we reduced f dot t ds, we reduced it to f dot dr, and the only way we could calculate it now was to actually f dot dr dt dt. So we did the dot product of the vector function with the derivative of the curve, basically the velocity, and take the integral like that. Today we're gonna figure out a nicer way to do this, a much faster way to do this for some vector fields, okay? For some vector fields which are relatively nice vector fields, okay? And I'll try to give some physical examples so that it'll make a little bit more sense. So today we're gonna start with a vector field defined in an open region D, and let's assume that for any 2 points A, B, so if this is our open region D, and take any 2 points A and B in D, and if the work integral f dot dr, the work done by the force field F on this curve, on moving an object from this curve from A to B, is independent, okay, is independent of A and B, and it's independent of which curve you choose. Okay, so any given 2 points, no matter which curve you choose, which nice curve, piecewise smooth curve you choose, it always gives the same answer, so it's independent of the curve, okay? Then we say F is a conservative field, okay? A conservative field. And in that case, of course, when F is a conservative and if F dot dr always gives the same answer no matter which curve we follow, then we say the integral is path independent, okay? So when it's path independent, okay, so the shape of the curve is not important. Where it goes through is not important. What's important is it's only its endpoints. So instead of saying the integral is over the curve, okay, we're only going to say the integral, it doesn't matter how we get from A to B. We're just going to say the integral is from A to B f dot dr. Now the question is, okay, so this is all nice, but how do you again evaluate this? That's what we want to get to. Now, for conservative fields, we can give as an example gravitational fields and electric fields. Okay, so a gravitational force, this F is not the field, G is the field. Okay, when you have a gravitational field G, the force applied, okay, on an object with mass m is m times g times a constant, okay, times a constant. So this is the force that you get out of it, okay? And for an electric field, for a charge with Q and electric field E, again, the force that that's gonna be applied on the object for electrical charge Q is gonna be Q times E times some constant, okay? So these are both examples of conservative fields. A field that's not conservative is like friction field, right? So if I just watch my pen, if I'm moving this from here to here, right, the friction here, and if I take a longer path to there, that's different, right? I'm going to spend more energy this way. If I go this way, this will be less energy, okay? So some fields are path independent, some fields are path dependent, okay? Gravity and electric fields are path independent. It doesn't matter if I'm raising this pen, the tip of my pen to here, right? It doesn't matter if I go straight or if I go around like this, okay? At the end, it's going to have the same potential energy, okay? And if I start from here and go do a loop and end up here, in terms of its potential energy did not change. It doesn't matter if I do crazy stuff like this and go back here, or if I do a circle and go back here, it stays the same. So it's path independent. Okay. So now we want to figure out a way. Okay, so the story for this section is how do we first of all figure out whether a given field is conservative In other words, its work integral is path independent. And how do we do that? And how do we actually then integrate the work integral? Okay, so we're going to concentrate on the first bit. Given a vector function f, if there is a field such that if there's a function, scalar function, such that the vector field f is the gradient of that function, okay, then we call f the potential function for the field f. Okay, so the small f is the potential function of f. Okay, so remember, f is a vector function. If it is the gradient of some other function, small f, then f is the potential function. This is the gradient function. Okay, so it's going to turn out our story is going to be basically that if your vector field has a potential function, then you're all good. Okay, it's going to be a conservative field. So as an example, let's go back to gravitational potential and electric potential. Okay, if there is a potential function f for a field f such that, okay, then if there is a potential function f for the big F, then the integral is always path independent. In other words, over C, f dot dr turns into a to b of f dot dr. And how are we going to evaluate it? We're going to say it's over a to b, f was gradient of f, that's the potential function, dot dr. And its evaluation is very easy. You just plug in the point into small f, subtract, plug in the point into small f. Now, where does this come from? This is going to be the fundamental theorem of line integrals. Now, the name should suggest the fundamental theorem of calculus. Okay, so it's just like the fundamental theorem of calculus. It's a very, very important theorem. And the intuition is the same. We said gradient of f is equal to f. So think about, I mean, this is very loose notation. I'm just trying to give you intuition here. Think about f prime gradient is like the derivative. F prime is kind of like f. So the fundamental theorem of calculus says whenever you're trying to take the integral of the derivative, you just get the function back, right? So it means that if I'm trying to integrate f, I'm actually trying to integrate the derivative of f, so I should get small f back. Okay, that's just the intuition. Now let's actually see the theorem in action, the actual statement, and how we would prove it. This is called the fundamental theorem of line integrals. I'm gonna abbreviate it to be FTL from here. Okay, faster than light speed, because well, the first letters fit, and second of all, it solves integrals so fast you won't believe it. So the statement here is given a curve. Okay, given a curve, we have a parameterization of that curve when t is between a and b, be a smooth curve between the points big A and big B. Let f be a continuous differentiable function, okay, with gradient field small f. Okay, so it is the gradient field. It's the gradient field of small f is big F on a domain D containing C. Then the integral, the work integral, is fp minus fa. So it's just basically what we said before. It's very easy to evaluate these. Okay, so if big F is the gradient field of small f, then it's very nice. The work integral is just fp minus fa. Okay, so let's go and do these. So gravitational or electric field. So a gravitational electric field is an inverse square force. So they are basically this force multiplied by a constant, and if this is the gravitational potential, the gravitational force field is going to be gradient of f. So we want to find the work done by f in moving an object along any smooth curve C from A 1, 0, 0 to B 1, 1, 0. Okay. Now we have to make a slight modification of this, and the C cannot go through the origin, right? When you get through the origin, this function is not continuous, it's not differentiable at the origin. So the curve cannot go through 0, because if you think about If two objects, right, are getting closer and closer to each other, when they are exactly close to each other, which they can't be because they have some volume or something like that, right? If they were right on top of each other, the gravitational force would be infinite. So you don't want to have that stuff. So you don't want this to be zero. Basically, you don't want it to go through the origin. All right. So in that case, the work integral is going to be c times f dot dr. We've already mentioned that the potential field was this. So, all right, that's going to be f dot dr is the same thing as gradient of f dot dr from a to b. That's going to be f of b minus f of a. So plug in b, you get minus 1/2. Plug in a, you get 1. So it's minus 1/2 plus 1. And you get a total of 1/2 then, okay? So minus 1/2 minus a minus a 1 is equal to 1/2, okay? So it makes it very easy. Now, if we didn't have this fundamental theorem of line integrals, we didn't use fundamental theorem of line integrals for every single curve between a to b, I would have to parameterize that curve. Then I would have to take its derivative. Then I would have to do the dot product. Then I would have to integrate. You know, it would be a pain. It just take too long, right? And we'd have to do that for every single curve from a to b, and you would keep getting the same answer. And then you would always have this nagging feeling, will the next curve give me the same answer or not? Okay, so this theorem takes care of it all. It says that if a potential function exists for your vector field, every single curve is going to give the same answer. And the way you do it is you just plug the points in to your potential function. Now let's prove the theorem, because the proof is nice and short. It uses the fundamental theorem of calculus. Okay. So actually, let's have the theorem here so that you can see it. Okay. So basically, what I'm going to do is I'm going to do the kind of trick that we did last time. We're going to look at df dt. Okay. Now df dt is df dx times dx dt plus df dy plus dy dt plus df dz plus dz dt. But what is that? It's going to be just gradient of f times dx dt comma dy dt comma dz dt as a vector. Now where the x is, remember, our r of t was gti plus htj plus ltk. Okay, so this is the x, this is the y, this is the z, and in that case this guy is just going to be dr dt, right? Okay, because we're only interested in what f does on the curve. So this simplifies, this is going to be dr dt, so this simplifies to gradient of f times dr dt. Okay, but gradient of f, we assume that was the potential function. F was the potential function for big F. So gradient of f is equal to f dot dr dt. So now we are all good. If we're interested in the work integral, okay, it's going to be over the curve f dot dr. Well, let's parameterize it. That's going to be from t equals a to t equals b, f of dr dt times dt. But we realize that f times dr dt is the same thing as df dt. So we're doing the integral of df dt with respect to t, while you're doing the integral of the derivative. So the answer you get back is f by itself, only we have g of t, h of t, and l of t. We have the curve plugged into it from a to b. In other words, of course, when t is equal to a, right? When t is equal to a, r of a is equal to a, because the curve starts from big A and curve goes to big B. So this is just going to be, once you evaluate, you're going to get fb minus fa. It's a very, very nice theorem. Okay. Now, the next theorem is one that we're not going to prove. Given a vector field f, whose components are continuous on an open connected region D. Okay, so I want to say a little bit here. You got to be a little careful about the assumptions of where your vector field is. In general, you want to have a simply connected region. Connected means it's one piece. Simply connected means it basically doesn't have any holes or anything in it, okay? It's a nice region, something like this. Maybe the three-dimensional version of it, okay? So let F be a vector field whose components are continuous on an open connected region D. Then F is conservative if and only if. When is F conservative? When are the line integrals path independent? If and only if it is a gradient field of some differentiable function F, okay? This I'm not going to prove. The proof of this one is a little bit more involved. So this says basically your vector field is conservative only when it is the gradient field of some scalar function, of a function that's not a vector function, it's just a function of x, y, and z. All right. Now, the next thing we are going to prove, the following three statements are equivalent. The work integral over a closed curve, over a loop, okay, when you do a loop, the work integral is 0. And if it's conservative on D. So if it's conservative on D, if and only if for every single loop, you get the work integral to be 0. That's it. And that makes sense. I just showed it to you. If I start from here and end back here, right, we're going to be evaluating the, if it's conservative, we're going to be evaluating the potential. So how much potential energy has this gained? Nothing. Doesn't matter if I do crazy and back up here. If I end up at the same point that I started, it's going to end up having the same potential energy. Whether you start from here and end here like this, or whether you go all the crazy stuff and end here again like this, how much potential energy have you loaded into this? Nothing, okay? So that's where the intuition comes from. And the other thing is, well, if it's a loop, the starting point A and B, they are the same thing. So when you plug them into the function, right, you're basically doing FB minus FA, but that's just FB minus FB, which is 0. Now let's see the theorem in action, okay? So I'm gonna do 1 implies 2 first. I'm gonna do 1 implies 2 first. So we are assuming that the work integral is 0 for every loop, okay? So, and we want to show that F is conservative on D. So let's just take any 2 points, A and B, and let's just take any smooth curve C1 and C2 between A and B. What we'd like to show is, what we want to show is that the work integral over C1 is the same thing as work integral of C2. In other words, it's path independent. Now, I have to use this loop idea, so I'm going to get a loop by parameterizing C2 the other way. Remember, every single parameterization gives us an orientation. So if this was C2, I'm going to say this is minus C2, exactly the other way from B to A. Then if I let C be C1 union minus C2, I get a loop, okay? Since we assumed the integral here is 0, that's going to mean, what's the integral? Well, it's the integral over C1 plus the integral over minus C2. But we already saw that this was the minus integral over C2. So all that has to be equal to 0, which means this integral has to equal to this integral, okay? So it's path independent. Now let's assume that it's path independent and use the fact that, show the fact that around the loop, the work integral has to be 0. How are we going to show that? Let's C be a loop. We have a loop like this, okay? And I'm just going to take any point. It's a loop from A to A. I'm going to take 2 points. They're just different points on this loop, okay? It doesn't matter where they are. They don't have to be diagonally opposite or anything like that, right? Well, this curve doesn't have to be symmetric anyways. This could be a very weird curve. So I'm just going to take 2 points. I'm going to call this section C1, the other section C2 on this closed loop C. Now, if I change the orientation of C2 again, they're both going to head this way from A to B, but we assumed that the work integral was path independent, okay? So this one was, the loop integral was C1 plus C2. Now that's going to be the same thing as C1 minus a minus C2. Remember, the minus signs would cancel each other, okay? But that's the same thing as minus C2 is, well, you're just doing this integral, subtracting this integral. Sorry, subtracting this integral. You're doing this integral, subtracting this integral. We already assumed that it was path independent, so this integral and this integral are the same. So once you subtract, you have to get 0, okay? So that's another characterization. Now we have two characterizations. We're going to get a third characterization next class. And what are the two characterizations we have? A field is conservative when, if and only if, it is a gradient function of some scalar function, okay? And a field is conservative if and only if every single loop, okay, every single loop, every single loop, for every single loop, the work integral is always 0, okay? No matter what kind of loop. It could be a crazy loop, it could be a circle, it could be an ellipse, it's always going to give you 0. Now, let's see the theorems in action. I just want to show you, I did this example two ways. I just want to show you how FTL, the fundamental theorem for line integrals, is really faster than light speed. It's just so quick when we're evaluating these work integrals. I'm going to compare it to the old way, okay? So I said, let's find the work done by the force field yzi plus xzj plus xyk on any smooth curve from A equals 1, 1, minus 2 to B equals 3, 1, 1. These 2 points, okay, any smooth curves. Now, because I said any smooth curve, right, if the problem is right, f has to be conservative. Otherwise, if it wasn't conservative, the curve, the type of curve you take from A to B would matter, okay? It would matter which curve you did. Now, because I say it's independent, okay, you can take this crazy curve if you want to, okay, or you could take something like this. It doesn't matter. Every single one of them are going to give the same answer. So we need to find its potential function. Now, I already know the potential function. This was pretty easy. If I look at, let small f be x, y, z, then its x derivative is going to be yz, its y derivative is going to be xz, and its z derivative is going to be xy. So we realize that gradient of f is actually this function, the force field f. So to evaluate the f dot dr, that's the same thing as, well, f is gradient of small f, a to b, gradient of f dot dr, and I don't need to do any integration. I just plug in f of b minus f of a. So f was x, y, z, plug in these two points. You can do 3 times 1 times 1 is 3. 1 times 1 times minus 2, that's minus 3. 3 minus a minus 2, that gives you 5. It's done, okay? For every single curve, okay, between A and B, we have calculated the work integral, and it's faster than light speed, okay? Now, let's try to do it the old way, okay? Let's try to do it the old way. See how much longer it is. Now, we can't actually do it the old way because the problem says, show that it is true for, find the work for every single smooth curve from A to B, okay? So obviously, if we try to parameterize every single smooth curve from A to B, right, that's going to take an infinitely long time because there's infinitely many curves. But let's just check it on the simplest smooth curve from A to B. Let's just check if we get the same answer. We get the answer 5 if we let C be the curve that's just the line segment from A to B. Okay, line segment from A to B. Let's see if it gives us the same answer. Well, let's parameterize the line segment from A to B. Remember, it's going to start from A, so it's going to be 1. 3 minus 1 is equal to 2, so it's going to be 1 plus 2ti. Plus, it's going to start from 1, okay, plus 1 minus 1, which is 0, so 1 plus 0t, so that's just 1j. It's going to start from minus 2, okay, plus 1 minus 2, that's 3, so minus 2 plus 3tk. Now, just check your work every single time to avoid calculation mistake. Plug in 0, you should get A. When I plug in 0, of course, I get 1, 1, minus 2. Great. When I plug in 1, I should get B. I get 3, 1, and minus 2 plus 3 is 1. So I get 3, 1, 1. I get B. So this is the correct parameterization. Okay. Now, if you don't remember how I got the parameterization for the line segment, you might just want to review our line segment section. Or in any calculus book, just look at the vector valued curves, okay, vector valued functions, and curves, this would be this is a curved line segment. This parameterization always works. So then to calculate f dot dr, I would need to do 0 to 1 f dot dr dt. That was the only way we knew previously how to do this. Okay. So what is f? Well, f was equal to f was equal to yz plus xz plus xyk. Okay. So I plug those in. Of course, I'm getting my x from the curve, y from the curve, z from the curve. When I plug it in, I get minus 2 plus 3t, 1 plus 2t times minus 2 plus 3t, because that's z, this is x, okay? And finally, we have just, we have xy, well, xy is just going to be 1 plus 2t times 1, so it's just this guy. So this vector is the f part, okay? So this part is the f part. What about the dr dt part? Well, dr dt is easy, right? It's going to be 2, 0, 3, 2, 0, 3. Multiply them together, you get minus 4 plus 60 plus 0 plus 3 plus 60 dt. Simplify it, you get minus 1 plus 12t dt. And that's going to be minus t plus 60 squared, evaluated from 0 to 1. And the answer is, again, 5. Now, I would much rather do it this way, right? Plug in just these 2 points into the potential function than doing it this way, okay? And doing it this way is actually not the end of the story, right? This just did it for the line segment. Proving it that this is going to be true for every single curve, well, that's exactly what FTL says, right? Because the function is the function has a potential, the function is has a potential function small f. Now, one thing that we haven't done is, I kind of skipped over, is for this f, when we have this f, finding its potential field, potential function was pretty easy. It was just x, y, z. It wasn't hard. So there's two questions. There's two questions here. Given a vector field f, if I know it's conservative, how would I find its potential function? That's something we're going to save for next time. Okay. And to start with, how do I know when I look at the formula of f, how do I know, without calculating its potential function, how would I know that it is conservative? That's again something we're going to do next time. So we have to be able to, the first thing is, before we invest in time on finding the potential function, we have to know from the formula some way of determining whether this guy is conservative or not. And then once we are pretty sure that this guy is conservative, we need to be able to find this potential function small f. So how do we do that? That's going to be for next time. All right, till next time, take care. Bye-bye.